Hello, my name is Andreas König and I'm the head of the Institute of Integrated Sensor Systems here at TU Kaiserslautern. We pursue the design of intelligent adaptive systems integrated into devices and appliances of industrial or consumer use. In particular, such integrated intelligence with advanced sensorial capability can be of service for salient assistance systems, for instance, in automotive or home automation fields. Today we are going to present to you our E-Taster-System with 3D printed multisensorial and autonomous lab-on-spoon and lab-on-fork units working as E-Tongues for automated degustation.
There are three application areas we focus on. These are food safety and quality assurance at the fork end of the food chain, living assistance to support people challenged by perceptive losses, and comfort functions related to nutritional, contents analysis and guided authentic cooking. The Smart Spoon by Dr. Ted Selker from MIT was a pioneering work towards consumer-based food assessment. Major technological advance from sensor to packaging makes the compact and mobile realization of Electronic-Tounges and tongues feasible. Various handheld devices have been announced in the last 2 years. Our lab-on-spoon and fork devices employ optical and impedance spectroscopy to extract fingerprints of the food samples. The optical spectroscopy is achieved with a MATSET MM-CS6CS sensor and several active illumination sources, including near-infrared range. The impedance spectroscopy is achieved by the 805933 chip. Low-cost viscosity and pH value sensing will be added next. In the information processing of the raw sensory data, we employ anomaly or novelty detection techniques, for example the no-glass method. This one-glass classification allows a very robust detection of any deviation from the expected ingredient. Further, we support standard multi-class classification to compare an unknown ingredient with our database. The computational intelligence methods applied also include case-specific dimensionality reduction of raw sensory data to improve and speed up detection. The E-Taster-Assistance-System is the heart of our ISE Smart Kitchen. A key module is the e-cookbook, which interfaces with our instrumented logs devices to check for food properties and preparation status. The logs devices feature the sensory front end with temperature, multicolor and impedance sensing, an Arduino Pro Mini microcontroller, USB and XP wireless communication, and an accu and a power management unit for system autonomy. Integration of energy harvesting for self-sufficiency is aspired in the next step. Now we are going to demonstrate the integration of multispectral lab-on-spoon in our e-cookbook module. For this aim, one of my favorite Chinese dishes is chosen, and the recipe preparation proceeds step by step, and checkpoints of ingredients prompt the user. The user fills the spoon with the ingredient, presses the button and receives the analysis result. In case of a correct ingredient, the e-cookbook proceeds to the next step. In case of a wrong or bad ingredient, e.g. adulterated food, the cooking process is stalled. The user can replace the ingredient and check the replacement, and on positive outcome move on. Lab-on-spoon has proven to be salient for liquid ingredient assessment, but a lot of food has a solid form, for instance meat, cheese or fruit, or comes in granular or powdery guise, for example sugar, tea, coffee or various spices. For these cases, the lab-on-fork has been conceived as the next member in the logs devices family. It has the same sensory capability as lab-on-spoon. Impedance and temperature are now measured by the fork's teeth. Multicolor measurement has been modified from scattered to reflected light measurement from the solid or powder surface. Now we will give one example of lab-on-fork application. We will try to distinguish several kinds of fish by lab-on-fork. This is also related to a common food adulteration problem, where cheap fish fillets are sold as the expensive kind of fish. This is hard to perceive for the human. We have already measured 3 kinds of fish, and we'll add one more kind to our example and database now. The fork is applied and measures color and impedance spectrum. The herring is clearly distinguishable from the previous fish in the database. In our work, we have applied logs to a richer variety of examples. A selection of representative applications will be given now, grouped in kind of food identification and state of food grading. For instance, we investigated electronic tea, wine, spirits, and beer tasting, as well as honey, meat, cooking oils, and various powder ingredients identification. Then we regarded rotting, contamination, or adulteration problems. For instance, the state of frying oil with regard to replacement, the incremental contamination of wine with a freezing agent, and the rotting process of milk were considered to show log sensitivity and applicability. Concluding, we have presented our E-Taster-Culinary-Assistance-System with the logs devices targeting on a large volume product for food safety and quality assurance at the consumer's end of the food chain, as well as life quality and health improvement. In future work, we will extend log sensory capability, for example by adding viscosity and pH sensing, and by extending spectral ranges of impedance and optical spectroscopy. Further aims are the achievement of an advanced, more naturally shaped and food-safe package, the conception of additional instrumented devices, and the extension of the ingredient and recipe database.